До нас доєднається Джесіка Вейд. Мені потрібна шпаргалка. Це фізикиня, співробітниця Royal Society University, викладачка функціональних матеріалів в Imperial College London. А от далі фраза. У широкому сенсі її дослідження стосуються нових матеріалів для оптоелектронних, спінтронних і квантових пристроїв з акцентом на хіральних молекулярних матеріалах. Це в широкому сенсі, якщо що. А дрібними мазками там взагалі, думаю, нелегко. Але ще вона пише в Вікіпедію. І от станом на лютий цього року у Вікіпедії було 2100 біографій її авторства. В основному вона пише про жінок-науковиць. Тому я не знаю, чи почує вона аплодисменти, але вона їх заслуговує. Будь ласка.
And she told me my great-great-grandmother is from Kyiv. And she was born just outside Kyiv, and then met my great-great-grandfather, and they moved through Eastern Europe to the UK. So I have a connection, both one of immense loyalty and huge strength and power to you in this really difficult time, but also a family connection. So today I thought I'd tell you a little bit about the types of science that I do, so the work that we do at Imperial on emerging technologies, particularly on these kind of new molecules that we could use for quantum technologies. And then tell you a little bit about this campaign and this story to try and better celebrate women scientists and why that's so important. Actually, like this whole festival, this whole workshop is telling you, it's just critical we really celebrate and value science at this time. You know, there's never been a more important time for us to have science and engineering breakthroughs to solve so many of the challenges that the world faces, whether that's the climate, whether that's getting people access to clean water, whether that's creating new innovations to make people safer, or whether that's coming up with new pharmaceuticals to tackle emerging diseases. We need science and engineering now more than ever before. But at the same time, we have this kind of global rise of misinformation and disinformation, which is perpetuating this kind of fear of experts and this rejection of lots of the ways of scientific thinking. So something I feel very, very passionately about is that we shouldn't only do the science that we do, but actually we should spend some time telling the public about the science and the innovations that we're creating. We should help other people come on board with that message and that enthusiasm and the excitement that you all feel because you're sitting in this room of extraordinary people, but everyday people might not get that opportunity. So I'll tell you a little bit about how I try, no matter what research group I'm in, to make them come on board with that journey as well. So I grew up in London. I grew up just next to a hill where you get a really, really beautiful view of London. This is in northwest London, actually. I actually finished high school, so finished school and went to art school for a year, and then ended up living in Italy and did history of art and Italian. But kind of at this time, I'd already started thinking I'm probably going to go and do physics eventually, but thought that this was a really great grounding in something that I know will have been a theme at this conference so far, but in that idea around kind of creativity, like how can you come up with a disruptive new technology? Who'll make the next big AI model? Who'll make the new way of developing a drug that's really, really active against a particular biomarker? You've got to be creative to do that. To build new instrumentation, to analyze data in a new way, you have to be thinking creatively. So luckily enough, I discovered I loved art really early and went and kind of studied those Renaissance masters in Italy, you know, the kind of the Da Vinci type people, the Caravaggios, the people who could really do everything. They could do metalwork, they could do architecture, they could do perfect line drawings. And they were allowed that space in their lives to be able to do all of those things. And I think something we do a lot in the UK, I'll be interested if it's in Ukrainian education too, although I feel you get it a bit better there, is we make young people choose really early on whether they're going to be a sciencey type of person or an arty type of person. And actually, particularly for young women, who were always told that they're more arty, that they're more into those kind of things than hard subjects like science or maths, it means that really early in young people's lives, we're pushing people out. So this is something I get very frustrated by. I feel passionately we should let young people do absolutely all the subjects they want. But we really need to encourage that mixture of science and arts to create really exciting new technologies. Well, anyway, sidetrack. But I started off in art and then I got to Imperial. So Imperial is this fantastic university that brings together research in sciences, so in biology, in chemistry, in physics, so the kind of natural sciences, also in maths and computing, huge focus on business and entrepreneurship and innovation, and then also medicine. But we don't have any other subjects at our university. We're a kind of science-focused university with that end product of wanting to make humanity and society better. And it's a really fantastic and exciting place to be. And if any of you can come across to London at any point, just look me up, send me an email, and I'll happily give you a tour around Imperial, or you can come and use the labs or whatever you want. So I started working. Hopefully this isn't too tiny on your screen. It's pretty tiny on mine. But I started working on these molecules called carbon-based semiconductors or organic semiconductors during my PhD. And it was some work that came out of this paper. This is from the 1990s. But this is a paper from a bunch of professors now who were at the University of Cambridge, some at Cambridge, some at Imperial. And they were looking at these plastic-like materials, and they pushed electricity in these materials, and they realized that these plastics started emitting light. And this was really unexpected, because at the time we expected these plastics to behave more like insulators, to not be conductive. But actually, not only were they emitting light, but the light they emitted depended on the chemical structure of what those plastics were. So we could tune the color of the light depending on the structure of those plastics. So we had these polymers, that's the kind of fancy chemistry name for plastics, that we could process like a plastic, but had the semiconducting properties of something like silicon. And this was really out there. And this paper makes it look like really old-fashioned technology. It looks like it's probably not something that's transforming everyone's life in that room and my life in the UK and lives all over the world. But actually, this observation in the 1990s is what gave rise to the OLED displays, the organic light-emitting diode displays that you have in things like a Nintendo Switch or an Apple iPhone or a Samsung Galaxy or a MacBook Pro. The beautiful colors that you get out of those displays are from these organic molecules. It also gives you the ability to be able to print these semiconductors onto flexible surfaces. So you can print them much like you print in the newspaper printing industry. You can print out things like these roll-up solar cells, and that you can then literally drive across regions that you want to get electricity to without having to connect to a grid. So this is this really transformative technology that not only gives you this huge market value through something like these OLED displays, but it lets you give kind of off-grid solutions to people who need electricity, particularly in communities where integrating electronics and things into the roofs is completely unfathomable to do. So you have this absolutely new pathway of where you can take these types of products. But also you can print circuitry, biocompatible circuitry, onto flexible surfaces. So you can start to come up with new ways to do things like biological sensing or imaging, because then you can print on some implantable chip that you can put inside your brain. Actually, there's some fantastic work with neurologists at the moment, which detects whether someone is about to have an epileptic fit and then pumps out a neurotransmitter and targets it to a specific part of the brain. And that's all because it's using these organic semiconductors, these carbon-based semiconductors. And I think this is amazing. I think it's just such a neat unification of chemistry, physics, materials, engineering, and all of these different disciplines coming together to say, hey, look, society needs this, so let's come up with an innovative new way to solve it. I think the kind of cool thing that my research group bring to it is this consideration of chirality. Chirality is a fundamental property, a fundamental symmetry property of shape and also symmetry. And chiral objects exist as a pair of non-superimposable mirror images, like your left hand and your right hand. And if you look at those and you're thinking, what's this posh word of non-superimposable? It actually just means that if you put your hands together, palm to palm, they're mirror images of each other. But if you put one on top of the other, then they're quite clearly not mirror images at all. Actually, no matter how much I try and rotate that hand on the top, there's no way it would be a mirror image of the bottom. And we see that kind of handedness across multiple length scales from the human-made to the naturally occurring world. So we see it at the subatomic scale. We see it in things like electrons and photons. Actually, these little purple spheres are to represent spin up and spin down electrons. We also see it in photons. So in light, this is twisted light moving towards us. So light can trace out a clockwise or an anti-clockwise spiral, depending on the way that it's generated. We see chirality in molecules, actually in lots of different types of molecules, in things like these biomolecules at the top, proteins and DNA have that coil-like, that chiral structure. These are some small organic molecules at the bottom called helicenes, and these are the types of molecules that I might work with. And what you'll see in this case actually is that the way that those rings, those 6 rings of carbon atoms are joined up, those molecules can't sit flat on a plane. They trace up a spiral. They're like a little spring, these molecules. So we have this molecular structure, which is chiral in itself. But we also see chirality in things like shells. So these are some actually fossils of all kind of snail shell type shapes. And you see the chirality there. You see it in pasta. We see it in the barks of trees, actually, that twist different ways, depending if they're from China or Japan. And also you see chirality in the light that comes to us from distant galaxies. So what this slide is trying to tell you, not only is chirality everywhere, you know, from subatomic to absolutely macroscopic things, but that also nature has chosen chirality as this design rule to make energy transfer processes or some kind of process more efficient. So if you look at the whole of the natural world, all of these biological molecules, all of these systems, all of these structures have chosen chirality as this really, really key design rule. So we started thinking, what about if we made our technologies chiral? What would happen then? And actually, if you make the molecules that emit light in things like your LED displays chiral, you make the display more efficient. So it means that you can get through one of the filters in the screen and just increase the brightness and improve the battery life. And there's some really exciting recent research that says that if you push electrons, if you push charges through a chiral molecule, depending on the handedness of that molecule, at room temperature, it will act as a spin filter. So only electrons will be able to get out if they're up or down, depending on the handedness of that molecule, which is really, really exciting for fields like quantum technology or spintronics, because it means you have a whole new opportunity to spin polarize those charges at room temperature without the need of magnetic fields. So what we're working on at the moment isn't really the LEDs anymore. We're thinking, how can we prepare those chiral, those twisted electrons? What can we do if we could entangle them? What could that mean for a quantum computer? Can we create a chiral molecule that will emit single photons that we could use for something like quantum photonics? And what happens when we put those chiral molecules inside a magnetic field? Do they change their interaction with light? And if they change their interaction with light, can we monitor that change to be able to understand the strength of the magnetic field? So this kind of happened recently, that we got really, really excited in thinking about these new applications, particularly in this space of quantum technologies. And that's because quantum technologies are going to completely revolutionize societies and economies all around the world. At the moment, about 30 countries have invested about 40 billion pounds into this next generation, this next industrial revolution of thinking not only about quantum technologies in terms of how can we prepare better semiconductors, or what can we do from a perspective of getting more accurate sensors, but how can we manipulate these phenomena like entanglement, like superposition, to make technologies that we've never dreamed possible before. And this has really, really excited me recently. You know, what can we do as physicists, as chemists, as material scientists to come in and say quantum has this huge potential? We first need to make it a fair technology that everyone can access. And then we need to be able to think about how we can make those technologies more efficient and more sustainable and operate at more environmentally friendly room temperature type things. As I mentioned, I'm also incredibly passionate that we communicate with the world the power and the phenomenal, remarkable properties of things like quantum technologies or other emerging technologies. On World Quantum Day this year, which all the physicists in the audience will know, we celebrate World Quantum Day on the 14th of April. Sorry, this is written in American language because they made the font. So you can see on the 14th of April, we celebrate World Quantum Day. And that's because Planck's constant, which is a very important constant for quantum, is 4.14 times 10 to the minus 15 electron volt seconds. So we celebrate it on the 14th of April. Don't ask me. Americans decided that. But we came together to celebrate Quantum Day at Imperial. I want to try and show you how fantastic we had all of these fantastic demonstrations to introduce the public to quantum technologies. We got the students to make this kind of quantum dictionary where they explained lots of complicated quantum terminologies. I made all of these fantastic cocktails. Maybe you can see how funny I am if I zoom in, but they were things like spin and tonic or a blockito or cube bra libra or a cold fashioned. So we have a lot of fun. And Megan up here, made this absolutely incredible kind of guided meditation around quantum technologies, where she walked us through things like, well, actually, firstly, we had music playing in the background that was all sounds we'd recorded in the lab. So we transformed sounds from the lab into this beautiful soundscape that was about half an hour of vacuum pumps and lasers warming up and the kind of click, click, click as the spectrometer goes on. And then Megan composed this kind of guided meditation that was, you're in a superposition of everything you could be and everything you are. And it just works so fantastically at introducing the public to this really abstract, weird phenomena and how we could use them and harness them in technologies. But something, as I mentioned, is not only how can we get more people excited about science, but how can we particularly get more young people excited about science? So ever since I was a PhD student, I've been trying out a whole bunch of different campaigns to try and get girls more enthusiastic about subjects like physics and engineering. I think, as I mentioned at the beginning, it's slightly different in Ukraine, that you have more girls studying physics, certainly at high school level, and maybe at the beginning of undergraduate, but you don't have many women in senior positions in physics across Ukraine. And in the UK, we have girls opting out of physics really early. You know, by the age of 16 or 17 years old, most girls, the majority of girls, have decided this kind of subject isn't for them, which annoys me so much because we know how fantastic girls and young women are at this subject. We know that there's absolutely nothing gendered in the way that people are talented in these kind of areas. And we also know that we need more diverse teams than ever before to create the best technologies possible. And so during my undergrad and then my PhD, I started doing as much as I could to try and get girls to come onto campus to experience how extraordinary these subjects were. And this was the first event. And hats off to the organizers of the science conference that you're at right now, because I know how much work has probably gone into planning it. I've never, ever done anything as beautiful or on the scale that you're currently operating at. But during my PhD, I invited about 200 schoolgirls into the physics department at Imperial. Here's our big old-fashioned lecture theatre. And I'm pretty sure this is the highest concentration of young women there's ever been in this physics department. And the most remarkable thing about this was 2016. And I still meet young women from this audience who are now, you know, during their biology degree or doing a PhD in engineering. I still meet people who came to this. But I realized pretty early on, actually, if I went to all of these places to give me money, they'd give some money to be able to support these types of activities. And not only could we do things for the girls, but also support their teachers and their parents so they could start to see what types of subjects these were and how brilliant they were. But then I thought I was limited. You know, it was long before we could connect on Zoom and quickly access huge classrooms or communities in places that we weren't physically. And I realized I was only limited to the type of people who could come to a university on the weekend, or the type of people whose parents would sign them up for an after-school coding class. And at about that time, I read this absolutely phenomenal book, which was called Inferior: The True Power of Women in the Science That Shows It. This book is by someone called Angela Saini. She's an engineer turned science writer, and she wrote this phenomenal masterpiece that looks at the true power of women and really how biases, misconceptions, stereotypes have been used to perpetuate this idea that women are academically inferior to men. Apparently, we're morally superior, but academically inferior. And this annoyed me so much. This book motivated me so much. Actually, I took it all around the world. I gave it to every time I'd meet a phenomenal woman or a professor or saw someone give a talk or whatever, I'd give them a copy of this book. And I realized, you know, I'm limited to who can come into this classroom. But actually, if I get a copy of this book into every classroom, that takes the story to a whole bunch of people. So I set up a crowdfunding campaign to get a copy of this book into every high school in the UK, and it took a couple of weeks. And you know, this is about 2 weeks on Twitter, at the high point of Twitter being a fantastic place to meet and to collaborate with other people, and manage to make it possible. I'm aware you're already over time and I have so many things to tell you, so I'll just tell you a little bit about my Wikipedia project and then hopefully have some time for some questions. This started actually a few years ago. So you probably all remember this amazing film Hidden Figures coming out in about 2017. So this was the story of the African-American computers at NASA, the mathematicians who enabled human spaceflight. And actually, I watched this movie. I hope you watch this movie. I hope if you've got children, they watch this movie, and your parents and your siblings watch this movie. But so did the US State Department. And they actually coordinated this International Visitor Leadership Program, this IVLP, themed around this movie Hidden Figures. And this was a kind of month-long trip around America with 50 incredible women scientists from 50 countries. And I went and represented the UK. And I met all of these absolutely sensational women and all of these absolutely remarkable scientists and engineers in every university we went to. And every time I'd meet them, I'd go home and I'd look them up on the internet. And lo and behold, they wouldn't have a Wikipedia page. You know, they'd pretty much be unfindable on the internet. There may be some small biographical information about them on a university website, but there was nowhere near as much as there should be. And then I started thinking a lot. I started thinking a lot about how important Wikipedia was. It's important not only as validation that someone's important or credible. You know, if you go online and you search for someone and they have a Wikipedia page, in your mind, you're kind of like, oh yeah, they're the real deal. They're a kind of big deal person. I should write about them. I should invite them on my radio program. I should invite them on my television program. But actually, Wikipedia is used by teachers. It's used by academic professors. It's used by doctors. It's used by lawyers. It's used by young people. You know, if we got the content on Wikipedia as true and valid and representative as we could do, then we'd do a big service to trying to make the world more gender balanced and to try and make the world better celebrate the contributions women have made. As of right now, about 1 in 5 biographies on Wikipedia are about women. So if you look at all of the biographies, this is English language Wikipedia, which is the biggest language Wikipedia. But if you look at whatever language Wikipedia it is, women are about 20% of the biographies. And this annoyed me so much. So since the beginning of 2018, I've been writing these Wikipedia pages. Oh, it comes up a little bit too quickly. You don't get the kind of sentiment of how long that journey has been. But I've been writing these Wikipedia pages almost every single day. It was every single day until I became a lecturer at university last year. So last October, it switched to about 3 or 4 times a week. And apologies, I'm trying to keep going, but people keep asking me to do other stuff. But I started to document and to write these biographies of phenomenal women scientists, of phenomenal women engineers, and to make that website more accurate, more equitable, and more complete. Just incredible things happen when you put things on Wikipedia, and I'll come to the end in a moment. This is just an example of a mathematician called Gladys West, who was born in 1930 in Virginia. When I started reading about Gladys West, it was February 2018. There was very little about her on the internet. She was born in Virginia. She studied maths at university. She went to a historically Black college and university, ended up working for the US Navy on the beginning of GPS. And then she became the person who made it possible for us to do navigation on any smart device. So she worked out how non-spherical planet Earth was, how far from a sphere planet Earth was. So you could put satellites in orbit around planet Earth and be able to track and accurately, precisely tell where you were where you were and how you should be able to navigate. Anyway, I put her on Wikipedia, February 2018. A few months later, she was honored by the BBC as being one of their top 100 women in the world. The US Air Force inducted her to their Hall of Fame. About a year later, the Royal Academy of Engineering announced that she was the winner of the Prince Philip Medal and Prize. They'd never in history given this award to a woman. So this was actually a pretty sensational thing to happen. And then I was talking about her nonstop, trying to get other people to learn how to edit Wikipedia. And this technology company said, oh yeah, next week, let's do another Zoom call. And, you know, it was the height of the pandemic. And I was like, I don't know if I can handle another Zoom call. But it was actually a Zoom call with me and Gladys West, actually sitting exactly where I'm sitting right now. So that's pretty fantastic for you to get the real deal of that. But I got to meet her and talk to her about this phenomenal legacy that she'd had on maths and this impact that she'd had actually on the world. So this is what I truly think. You know, the science, the technology that you're hearing about over these 2 days, organized by these remarkable people, is the technology and the science of the future. You know, this is how people are going to live. You are shaping the future of the universe by the ideas and the voices that you hear this weekend. And we have a responsibility to take that inspiration, to take those stories to as many people as possible. We definitely need to better represent and to better celebrate the phenomenal contributions of women in all walks of life. I strongly believe it for science, but you name it, whatever discipline it is, women are under-honored and under-celebrated. I'll close with a quote from Barack Obama, because I feel like we need to celebrate all fantastic politicians at the moment. But change will not come if we wait for some other person or if we wait for some other time. And maybe, you know, you feel it a lot in this room right now, but we are the ones that we've been waiting for. So I'm going to say super massive thank you for everyone. I've got the date wrong there. That's not very well done of me. But thank you so much for listening to me. Thanks so much for organizing and inviting me to this fantastic conference. And hopefully I get to meet as many of you as possible next year. But if you have any questions, then that would be fantastic too. So thanks so much for having me.
Thank you. I don't know if you can hear us, but thanks a lot from Kyiv, Ukraine. Thanks, Jessica.